Bom dia, good morning. So let's go back to the problems we were studying. So I'm going to do, due to some of the questions you were asking and we were talking last time, and also so that we have for people watching, I'm going to show a little more of the mathematical modeling, okay? So that hopefully you can understand better how the mathematical modeling goes into the numerics, which is our main goal in this course, right? So as I'm saying, these last lectures, which are more advanced, it's like how we go from math modeling to numerical modeling to scientific computing, where scientific computing is to understand better the PDEs, to understand better the properties, physical properties of the problem, and so on. Okay, so in this second article that I'm showing to you, I showed to you, you see the system up there is the system we deduced, and I showed you briefly last class how to deduce the system. We see this in more detail, as I mentioned, the PDEs and applications course. In the fluids course, we see a little bit in both. So those interested can look at, at the PDEs and applications course that we also have in English, the fluids one we have in Portuguese. And now we're going to be using a theory, right? So we're going to be basically, now let me put it here. Maybe I haven't written this completely. Let me write on the board. Yes, here it is. So we're going to use, so basically in the paper projected, we generalized the theory of Berliand and Burridge wave motion is the name of the journal, and here I got this to check. Wave motion, volume 21, 1995. And it's for acoustic waves. And let me put the title so I can mention too. It's the accuracy of the authority entity approximation, let me abbreviate like this, in highly disordered stratified media. So this paper is for acoustic waves, and for us, in terms of PDEs and so on, is basic for a hyperbolic system, okay? So Authority and Anstey were two geophysicists, right, studying the crust of the Earth, where the first ones, I think, to identify that as a wave moved down to this layered medium modeling the crust, there was an apparent attenuation. The wave would be attenuated. And they try to explain how, and then mathematicians coming with these two and Papanicolaou and collaborators showed mathematically how this attenuation took place, okay? So how it was taking place. And they showed it, for example, with this stratigraphic, because of the stratified medium, stratigraphic filter that I mentioned last time, okay? So you see, so therefore, in the math, at least in the math community, and when I first heard about this, we started calling this, and in some papers it actually had the ODA approximation. ODA approximation, which is the approximation that looks like the wave. You have a hyperbolic system with no damping, no dissipation, no nothing, But if you look asymptotically to the wave moving through the disordered medium, which in some papers is the disorder medium is modeled as a random medium, okay, you see this attenuation. So you see the title is very revealing. So the first step we wanted to do is to generalize this for a dispersive equation. So that was the first step of Juan Carlos' thesis. So look there, and then Juan Carlos was actually my first PhD student here at IMPA. So the equation upstairs, the first one, is this using conformal mapping, blah, 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 the whole story I told you, simplifying potential theory into a system, Boolean-esque system, that is a weakly nonlinear, weakly dispersive system. Weakly nonlinear because there's an alpha over there, which is like order epsilon, and weakly dispersive because there's the beta over there, order epsilon. But since the acoustic theory is linear, so let's do it step by step. Let's not make our life too complicated. So numerically, actually, Juan Carlos programmed the full system of equations, okay? And then, you know, in the numerics, you can put alpha equal to 0, or you can put alpha very small, much smaller than beta. That's how we played with it. Well, why did we put alpha much smaller than beta? We said, let's leave alpha in the computations. After we said we noticed everything was fine, let's leave alpha there just to see if the nonlinearity doesn't do anything crazy. And it didn't, right? And we put beta small, like, for example, 0.03, whatever, and the other one 10 to the minus 5, alpha 10 to the minus 5, and we check things. But the equation we want to do the theory is the one just below, 2.5. So look at 2.5. If beta is equal to 0, it is a hyperbolic system. If beta is small, it's a weakly dispersive system. If beta is small, it is a dispersive perturbation of the equation like Berlian and Burge. So that was the idea. So we said, let's try to do some theory using the ideas that we found in Berlian and Burge, see if we can sort of generalize, adapt it to this system. Let's see what we get, and then let's do the scientific computations to illustrate the theory and to see how far the approximations go, because the theory has asymptotic approximations. So I want to tell you a little bit of this story because I think from the conversations we were having, and maybe this is the same thing people that are watching, will help you understand better the phenomena, the physics. I mean, I mentioned to you, right, I think not here in the video, but after class, that the math helped my own intuition. I like physical intuition. I think it's important in some problems. I didn't have it at the beginning. It was acquired, the intuition, from the mathematics and from, as you know, from the scientific computing, doing simulations, doing experiments in the computer. You do something wrong, you fix it, this and that, and suddenly you're doing, I mean, the code is correct, but maybe you're doing parameters wrong and you start understanding better the physics through, right? And this is something very important, through the simulations. Okay, let me see if I can do it here. Let me see just a second if I can, with this mouse, roll it too. Yes. Huh? Let me, yeah, okay, let me make it bigger. Sorry. Okay, is this a little better? Okay. Sorry. So let me do something. Let me write this system for us to remember. Oops. Yeah, here it is, on the blackboard. Okay, so this is the system. Do you remember what M is? M is the square root of the Jacobian of the change of variables. Okay, now let's try to do some theory. So we're going to do some change of variables in the following way. So C0, which is the variable speed, is equal to square root of 1 over m. In the mapped domain, just by checking the eigenvalues of the if you make beta equal to 0, right? I think I've showed you this at some point in this course. We saw this in the PDEs course. If I make beta equal to 0, you check the eigenvalues here, and you see the propagation speed. Okay. Hope that window's a little loose. Okay. Is there? Let me see. No, I don't know. Não sei. Melhor não. So, and then, do you remember what x is? So x is, then we're going to use the x variable, which is which is integration of c. That's it. Which is travel time. Right? I've shown some of you have seen this in previous course, but maybe not in this course. I don't remember I've seen this course. So this is called travel time. Right? Look at this. This is the units of this, since this is speed, the units of this is time over length, right? And I'm integrating over length. So if I cancel this, the units of this, it's the units of time. Okay? Another way to convince yourself is like this. If I'm traveling and I'm integrating 1 over kilometers per hour, and I want to say, I want to go from 0 to some distance L, right? So this is going to be kilometers per hour, 1 over kilometers per hour, times distance is going to tell me how much time I took from one place to the other. Okay? So that's why it's travel time. Now, mathematically, this is a trick that was in the paper by Berlian and Burge. So when you do this change of variables, you write your system, as you see in 3.1, you write your system of equations in terms of travel time, which is x, and clock time, which is t. It looks like the system got a little more complicated. It does a little more complicated. And then you do this change of variables where r and L means this. R means right-going mode, and L means left-going mode. Okay, so we have our topography. Let me put it just like this. So this is R, this is L, because there's reflection and transmission. How do I convince you about that? Well, you're going to see in just a second. So we do that change of variables. I'm not going to show it to you in all detail. We see some of this in other courses. And then look at this equation here, 3,4, which is about to appear. Look at equation 3,4. Equation 3,4, let's do the first exercise. Don't check the details of the coefficients. It doesn't matter. So we have variable coefficients. If beta is equal to 0, you see, if I have no dispersion, if beta is equal to 0, P and Q are equal to 0. So forget P and Q. And if I have a variable speed, little r is a variable coefficient, and little r is called the reflectivity. So let me write this for you so you see why. I do this in some courses. I did not do this here. Is it plus or minus? Minus. No, let's see. Yeah. Okay? So this is the case beta equal to 0. So what does this say? Okay? Now let's think also that our medium is constant. So for constant medium, R of x is equal to 0 because this is equal to 0. The derivative, the medium, right? The speed does not change. So if that happens, what do you see from here? So in this case, we have RT plus Rx equal to 0, LT minus Lx equals to 0, which confirms that R is a right-going mode, L is a left-going mode, and they do not talk to each other. It's a linear problem, it's a superposition. This guy goes this way, this guy goes that way, and they don't talk to each other, okay? So in some problems, like for example, the problem that Christian is studying for rivers and so on, you can rewrite things in the way that over a piece of the river, there's information going upstream and information going downstream, right? And in the nonlinear case, you can write that too, even though I'm not showing it here. And in the nonlinear case, for hyperbolic nonlinear systems in general, you give actually these guys, when they're constant over characteristics, you give them the names of Riemann invariants, right? It's written in a slightly more complicated way, but it's the guy that travels over characteristics without changing. Okay, fine. This is the way Berlin and Burge write things. But look, now let me show you two things which are important. From the PDE's point of view, and numerically, it's important to have this in mind. If I have the reflectivity, which means here, there's something that's going to come this way, and then it's going to reflect back because of the medium and so on, okay? I'm going to have now Riemann invariants, and I'm going to abuse of the terminology, Riemann invariants that are not invariant anymore, right? So it's an abuse of terminology. Why they're not invariant anymore? Because the other guy takes energy out of this guy, right? Because there's a wave coming to the right, and then it bounces to the left, and then it comes back, and so on and so on. So this reverberation, which is a terminology from acoustics, right, makes that these guys are not invariant anymore. Okay? Another thing. Now look at that equation up there, 3.4, and make R equal to 0, right? Which means you have a flat bottom. You don't have a reflectivity. Make R equal to 0. C0 is going to be a constant. Okay? So in P and Q, C0 is a constant. Okay? So Q is equal to 0, but P is not equal to 0. Okay? So therefore, in that case, P is order beta. So if beta is small, make in your heads beta equal to epsilon. Then what do we have for the R equal to 0, but beta equal to epsilon? We have this. Now let me get the signs correct. It's going to be equal to epsilon some term here. I'm not going to write the whole term, xxt. And the other one is going to be also epsilon, the same term, xxt. Okay? So what does this say? So this is the weakly dispersive term. Okay, so now what does this say? What does this say? And actually we can do something kind of similar in the nonlinear cases, is that when I have dispersion, okay, I don't have Riemann invariance anymore, right? Because it's not 0. But I can say that the Riemann invariants are slowly varying. So again, abusing of the terminology invariant. They're not invariant. I call them the Riemann invariants because they're a nice object to deal with, but they're slowly varying along the characteristics. Okay, so very good. Another good thing to know. So if then you play with these guys, so now we take ideas from Berlin and Burge, where now we have the terms P and Q that Berlin and Burge, these two authors here, did not have. So in some sense, our equations are a perturbation of their equations, but we're going to use their ideas to see if it works. And I'm not going to tell you all the technical parts of their paper. You know, it's not that difficult to understand, but it's not straightforward either. And it's PDEs, not numerical PDEs. But I want to show you a little bit of the modeling. So what they do then is that, okay, they now get these equations. They're going to be more complicated. What's happening here? Oh, I'm going the wrong direction, sorry. Okay, you can write it like this. They do another change of variables. So I'm not going to get into the details. They do another change of variables. They use that variable tau that you see up there, which is called the delay variable. Why is it called the delay variable? Because t is just a regular time. So let's call it the clock time. X is the travel time. Okay? So if t minus x is non-zero, it means that there's a delay between the clock time and the time that the wave arrived. Okay? But mathematically, it makes life simple if you write in terms of tau. I'm not going to get into details. And then they do a Fourier transform in tau. They decide it's convenient to do that in tau. And if you do the Fourier transform in tau, as you see at the end, that f hat, okay, the system becomes, it looks at first more complicated. So all the hats here are Fourier transform in tau. And at the end, some manipulation and so on, you get ODEs. Where is it? Here in tau. I think I went too fast. Oh, I won't be able to show everything. So you get these ODEs. So maybe let me write it here for you. These are two coefficients. I'm not going to get into the details. Just so that you get some idea. I'm sorry because it's not really very comprehensive. What's the gamma? And I forget what's gamma bar. No, it's zeta bar. Sorry. But just variable coefficients. Wait, because it's complex, I think, yeah. So it's a conjugate. And then this is an OD, right, that you make some approximations. There's some technicalities. So I'm being bad in terms of the details, okay? So what is the message here? Let me go back and simplify the message for you, or else I'm going to put you to sleep with all the details. The message is, we get this system, right? The system, we rewrite it in terms of right and left variables. We do some changes of variables also in terms of time. in a way that's convenient to do a Fourier transform, and then we get that OD, okay? From that OD, it is convenient that you write the following. So the asymptotics gives us that the OD, that R asymptotically is this. Or let me put it this way. So asymptotically you can show, so what is the main idea? Asymptotically you can show that this to leading order is a Gaussian multiplied by the Fourier content of the initial data. Initial, let me put it like this so it's better, wave elevation. So what does that mean, right? It means that the right going wave to leading order is a Gaussian filter or the heat equation or an apparent diffusion of the wave data. Okay, please ask me questions because I'm going with some details, but not all details, a little fast, but so that we can appreciate the numerical simulations, okay? So I think before I show you the numerical simulations, now today I'm going to show you the numerical method, because some of the simulations I showed you last time, I will repeat them, but first let me show you the numerical method, okay? But up to here, does this story make at least some sense? You don't have to understand everything, because it's impossible to understand everything, because I'm not giving you the details. But I want you to have an idea of the story, an idea of the research project, an idea of a research project that has some theory and some scientific computing, numerical modeling, and so on. Okay? So feel free to ask questions. Okay, now let me go maybe to the numerical method, and then we'll come back to I will repeat some of the simulations. So these are results, blah, blah, blah. Okay. So how do we solve this problem numerically? Okay. So we're going to actually solve in the computer the full nonlinear equations, but we're going to put the epsilon equal to 0, the alpha equal to 0, or at a very, very small value, okay? So how do we solve this? So the initial profile is going to be a Gaussian or a solitary wave, and here's the numerical method. Okay, maybe I'll write it on the board so that we can keep it. So let me write it here. We can write our equation like this. Look, eta t is equal, I'll repeat it because I'm going to end up switching pages, right? Where E Okay, so let's come here to this board here. So look at this. This is just a way to write our system of differential equations in a way that we can use a numerical ODE solver. Okay? So right now I'm not quite doing the method of lines. I'm just sort of manipulating terms so that we can see an ODE solver. Okay? So look at this. This is so that it looks like an ODE. But of course it's not an ODE because we have partial derivatives here and we have this right-hand side here. Okay? So this is just so we can sort of identify what would be the vector field of an ODE. Well, what I'm doing is I'm getting my original nonlinear system, and everything that does not depend on time, I'm going to throw it to the right-hand side. Okay? So we can think of the method of lines. So here it is. E is this guy that I just threw to the right-hand side. Of course, this is a PDE, so I have this. Okay? So if I know how to discretize this, particularly if I know how to do this derivative, right, I have the vector field of my ODE. Okay? So this part is simple. And I can do my derivatives either in space or, it's in space. Either finite difference or spectral method. You know, Juan Carlos did first, I think in this paper, finite difference. In another work he did spectral method. So basically you can do this is just a difference of this guy. Okay? In particular of this guy, let me write like this, a little different in square brackets. Okay? Here, I also have a derivative in time. I think I'm typing. Derivative in space, sorry, which I do finite difference, not in time. Okay? So if I compute this, I have the vector field for this guy. Now, what is capital V? Let me highlight this capital V. This is a nice trick that we used. So the numerical method is by Kirby and Way. Okay, it's in the references of paper. And they do this nice trick, which is the following. Recall, look here, we can actually see here. This is the linear part. We have time here, and we also have time here. Okay? So, and actually when we have dispersion, one of the part of your reading exercise of the KdV is how to see the KdV dispersion term and use an integrating factor to get away with the stiffness problem. Okay? Here it's another strategy to deal with the dispersive term, because the dispersive term of the KdV is xxx, and here it's xxt, right, or xct, which is a little bit in the style of the BBM. Okay? So the trick that Kirby and Way use are the following. Look, I want to get this time here from the dispersive term and put it together with this guy so that it looks like an OD. So he does a change of variables. They do a change of variables. Let's call V this guy, because VT is going to be UT, U, CT, exactly that guy over there. Okay? So their trick, and actually we tested and they worked very well, it's a nice trick, is to rewrite the problem in terms of V. Okay? You evolve with a numerical ODE method. Could be predictor corrector or Runge-Kutta, doesn't matter. Okay? You evolve eta, I think we used predictor corrector, Juan Carlos used, so you evolve eta and V, computing the vector field, okay? And then after you have evolved V, you actually need to update U, because you're going to need U here. So how do you update U? You update U using this elliptic equation here. Look, it's an elliptic equation because it looks like a 1D Laplacian. How do you do this? You do this by writing it in this way. Look. let's see if I write like that. Let me have a drink of water and see if you understand what Wei and Kirby and I am thinking. I mean, what's the idea? Now that you are specialists in numerical PDEs. Yes or no? Yes, right? Yes, of course you are. You're getting experience, but you're already experts in numerical PDE. So I'm going to stay away from the backboard, but you look at the backboard, okay? So the trick of Kirby and Wei is very nice. They want to put all the time evolution terms on the left and write the rest on the right as if it was the vector field of an ODE, and then we can think of the method of lines, right? We first discretize in space, and then we evolve in time. Okay? So think in your minds, and that's a good exercise, think in your minds that we're first doing the very first time step. We're going from time 0 to time 1. That's the way to organize the algorithm in our minds. Okay? So if I'm going from time 0 to time 1, right, I need to know my vector field. If I have an explicit method, let's think of an explicit method. I need to have my vector field at time 0. Okay? So at time 0, I have U0, eta 0. U0, eta 0. I'm good, right? Let's double check here. This is the guy. This is a variable coefficient, which has information of the medium. I have eta 0, U0. I can find its derivative at time 0. No big deal, whatever. And here, for f, I also have U0 and eta 0 and U0. I also compute the derivatives. Boom. I do my evolution scheme. And I get, after I do my evolution scheme, I get eta 1. But then I get V1 and not U1. Okay? Good? All right, everybody okay? Melvin, everybody okay? Right, so ask me if you have any questions, okay? And this is a good way to start the algorithm in our minds, to see, oops, I have to calculate this. No, oops, I still have to calculate that. Okay, but now I have V1. Look, I have V1. And I need to compute U1 so that I can now, in the next step, have U1 and eta 1, so I can evolve these guys to step number 2. Okay? But I'm not ready for that. Well, but I have a simple problem to solve, which is this time-independent problem due to the change of variables. But now, look, this was the definition of my change of variables, and now I reverse this equation. Why? Because I'm going to think as this guy is known because it's V1. This guy is known. So this guy is like the forcing term, the right-hand side of an elliptic equation, which is 1D Laplacian plus U, which is like a 1D Helmholtz equation. Okay? You see that? Okay? The 1D Helmholtz equation, right? Helmholtz equation is usually something like this, V equal to F. Okay? So this is an equation that's an analog of a 1D version of this guy, maybe with the signs here just changed. I did it wrong. Okay? But now, how do you solve this? You're the expert. How do you solve this? And propose something the most simple way. And I think the most simpler way that you're going to propose is the way we did it. So this is known. Okay? So this part here is known, is the right-hand side, because I just computed through an ODE solver. But now what I need to do is, by solving this equation, right? Let me erase the end, see if just facilitate. Right? This is the one I'm doing at this instant of time. I want to find U1. Let me actually put it like this, so it's U1, U1, and I've just computed V1. So how do you solve this? Let me give you a hint. This is actually going to be a system AX equal to B with a tri-diagonal A, matrix A. Do you see what I'm saying? You want to say it, Marcio? Yeah, exactly. Do a center difference for this guy, exactly. See? You know, we've done this for the heat equation, Laplace equation. Use a center difference for the second derivative, right? This means I'm going to have a matrix which is tridiagonal because this guy is evaluated at the node I. This guy is going to be evaluated at the node I minus 1, I plus 1. Boom. That's it. This is the B. So it's going to be AX equal to B, right? Where the matrix A is going to be tridiagonal. In MATLAB, you tell MATLAB it's a tridiagonal matrix. So MATLAB even takes advantage of that. You invert this very quickly. I mean, you solve this system very quickly. And then you have U1. And then at every time step, you have to do that, right? So let me rewrite it as we had before. N plus 1, N plus 1, N plus 1. Where this N plus 1 here, we already got it from solving here. Okay? Cool. So that's the way to deal with this cross derivative here. This cross space-time derivative of this term, which at first looks kind of a bit weird. How am I going to deal with this? I like this trick of Kirby and Way very much. Okay? So this is very nice. And then what we had to do, the first thing that with Juan Carlos we had to do was, okay, are we solving this correctly? Do we have the right things? So what, okay, so if I was working with you on this problem, instead of Juan Carlos, what would be the first simulation you would do to test this method that we're solving here? What would be the first simulation? Say, okay, right, any one of you, and I would say, okay, before we put, so let me give you a hint. Before we put the topography in, the crazy topography, right, please test this method to see. I had never used this method, Way in Kirby and Way. So I told Juan Carlos, look, let's test this method. Let's see if it is, he actually came with a few, I said, look in the literature. He came with a few papers. This one I think I knew, I kind of have found. He said, look, I said, I have this one as a suggestion. Check some other ones. I know Kirby's a very nice, very good guy. I never met him, but he's a very good guy, very productive. He's actually a civil engineer, but very sort of does many papers in Journal of Fluid Mechanics, and so a very good guy. So let's test his method. And then Juan Carlos said, yeah, I also prefer this method. Let's test it. So what is the first test we did? Or what is the first test you would do? First one is beta equal to 0, right? Because if I do beta equal to 0, I'm actually not going to have to test this, right? Because look, let's come over here. Let's first, this is a guy which even in the flat bottom case is a tricky guy, right? So let's test our method first with beta equal to 0. This guy away. And then the second test is with this guy small. Good? So let me show you the pictures. That's exactly what we did. And if this guy is 0, what is the initial condition you're going to put? Recommended. What's the first initial wave profile, initial condition would you choose to test the method? Gaussian. Exactly. Okay? Gaussian. And then after everything works well, and of course it's going to work well because it's published in the paper and I'm going to share with you, we're actually going to allow for alpha to be small. And instead of putting a Gaussian, we're going to put a small solitary wave where nonlinearity and dispersion are at the same level, balance each other, so that you have a traveling wave. Okay? And then we're going to test the solitary wave with the linear apparent diffusion theory, just for fun. And it was quite fun because it actually worked, even though the theory is a linear theory. Okay? So those are the steps we're going to do. Very good. So you guys have the spirit of the scientific computing project. Oops. let me put the figure here. Let me check here in the paper I have, just to make sure this is the first simulation. Okay, so what we did here, okay, so we're checking things for the flat bottom case. Okay, so I remember what we did. Why it's not moving? Maybe it's the mouse over here. Let me see. Okay, I think this is good. So the first simulation upstairs is, let's pay attention to the alphas and the betas. Okay, so we're solving we're putting the full nonlinear boosted system. So over there we put a Gaussian. You can see the Gaussian over there, right? And we did alpha equal 10 to the minus 3 and beta 3/10 to the minus 2. So the nonlinearity is very small, and the dispersion is a little higher. So we see that's the initial profile in the dashed line. And the solid line is the numerical solution, and the open circles are the exact solution. So the exact solution there is basically computed, if I recall, using array function and computing it numerically, because array function doesn't have a closed form. It uses a Fourier representation or whatever, okay? But look, it's very nice. The numerical method, so what is this good for us? Okay, so let me check with the experts also, right? Because it's a good exercise. So don't smile, let's get working, right? Check with the experts. What am I checking here with this case? I have a flat bottom, okay? I have a small dispersion, and I'm putting the nonlinearity even smaller, but I'm leaving it there just to see that it is not effective. That part I'm going to help you. So I'm leaving not effective in both ways. Not effective in messing up, generating some instability, whatever, numerically, but also from the scientific PDEs point of view and physical point of view, it's there, but it's not an actor. It's not participating in the dynamics. Okay, that's what I mean by putting not switching off completely the nonlinearity, but not allowing it to checking. The word is not allowing. It's like checking if it's not really participating in the dynamics. And it isn't, because I'm checking when I say exact solution. I'm checking it using the array function, which would be the exact solution from the linear dynamics. Okay. So when I do this numerical simulation, what am I checking? What am I verifying? Help me, the experts here. What are the words? Or if you're the referee, you would say, okay, the author has verified bling, 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 blah, blah, blah. What is that? Right? We put this in the paper for the referee to feel comfortable with our, right? And the readers be comfortable with our simulations. And the first one is to show, now I need your help. What do we show with this when we present this result for the flat bottom and with these values? So let me help you. First, number one, do we have an effective, that means, also let me show you. The time interval is 40, right? So basically, we want the pulse to have traveled, with this scale, it traveled, look, it went to 0 all the way to 40. So it traveled 40 units of propagation distance for a wave that's maybe the width of the wave is around 1 or 2, right? If it's a Gaussian, basically the standard deviation is about 1. So it traveled quite a long time, and that's the time we need for it to interact with the random or the disordered medium for the parent diffusion to appear and so on. So, but here there's no random medium. So we're showing that over our interval of interest, which is the propagation interval of interest, is there in a numerical diffusion that's noticeable? That's the first question I ask you, the experts. What would you say as a referee that our numerical method, with the grid we've chosen, right, with the time step, and as referees to our paper, would you say that Munoz and Nachbin showed a result with or without noticeable numerical diffusion? Sorry? Without numerical diffusion. Okay. And why do you think there's no numerical diffusion? The theoretical, so very good. Because the numerical solution is right on top of the numerical solution. And now is an important thing too. The exact solution has dispersion, legitimate dispersion. On top of the legitimate dispersion, I could maybe have also, and of course we did this on trial and error because we don't quite have a theory, we could also have numerical dispersion, sorry. So note that when we go to our hard test drive, which is with a variable topography, and where we're going to check for effective diffusion, apparent diffusion, we got to make sure that the apparent diffusion is mathematical, is physical, it's not numerical. And also, since we have dispersion, we want to know that the dispersion is legitimate dispersion. There's no, effectively speaking, numerical dispersion. Of course, there are numerical errors, but we want to keep the numerical errors to a level which is unnoticeable on the solution so that we can infer mathematical properties of the solution and also its physical consequences, right? So here, graph number 1, we're showing that basically there's no, the dispersion is correct, right? And there's no noticeable numerical diffusion, right? Numerical dissipation. Then figure number 2, the one below, look, I put the dispersion, not me, actually Juan Carlos did, we put the dispersion coefficient now even smaller. It's 5, 10 to the minus 1, 2, 3, 4, 5, whatever, 4, okay? So now the dispersion is even smaller so that also we can convince the reader, in first case the referee, that look, now in the effect, at this value, there's basically, mathematically there's no dispersion. You see the Gaussian with no oscillatory tail. And you know exactly what I'm doing because of that exercise you did for the shock and so on, where you can see when actually there is a legitimate dispersion due to the method, blah, blah, right? The shock capturing. So this second picture here shows that actually we can control the parameters so that there's no diffusion, no dispersion. And also we wanted to show that actually for our own learning, that we don't have to put beta to equal to 0 for the dispersion not to be noticeable. You can put it very small, leave it there, and it will only, the dispersion only, for this value here of figure 4.2, the dispersion will be noticeable when? That's, the experts help me here. When will I notice this dispersion? Because it's non-zero. There are two answers for that question. For this beta 0.0005, right here, you're good with me. I'm not noticing dispersion, right? And this is a good, very good, this is a very talkative class, but it's very good to develop, control and insight into these problems. So with this same value of these parameters, how can I make dispersion, because beta is different from 0, how can I make dispersion appear in this problem? I can think right now of 2 ways. Let's see if you help me. And I'm saying 2 ways for maybe to help you, give it a try. Even if you guess wrong, it's no problem. Here it's practice. A bigger? Yes, that's one way. Bigger time, which also which would mean maybe a bigger numerical, interval. But I don't know, I think we had periodic, if we have periodic boundary conditions, the wave would just come back, but the bigger time is the right answer, which is the same thing as bigger propagation distances, right? Because eventually, the dispersion will start appearing, and the little tail will start appearing, as you saw. Okay, very good. What is the second way of maybe making the dispersion appear? At least the one I'm thinking still of another way that it would appear. Changing? No, you can't change. Yeah, no, okay, that would change, yeah, but you're not allowed, okay, sorry. My question is, you're not allowed to change the parameters of either the grid, okay, or the parameters alpha, beta. You can change one thing, but not the numerical scheme or the discrete model, okay? The discrete model you cannot change, which means you cannot change grid size or alpha, beta. You cannot change that. But there's one thing you can change to see dispersion with these parameters. Initial condition, very good. And then what would you, very good. Those are the two things. And then what would you do, what will you do with the initial condition to see dispersion? This, you see, what I'm doing with you is what in Brazil we call, from football, treino com bola, right? Which is, in English would be scrimmage. You're practicing with a ball, pretending it's a real game, even though it's a practice, because it's a very good mind exercise. So how would you change the initial condition to see dispersion, say, in this time interval, right? Melvin gave the right answer. Now keep the same time interval, but change the initial condition. And I'm going to tell you, don't change the function. Let me force you, stay with the Gaussian. How do you change this Gaussian to see dispersion? Right, or else the question becomes a little too vague. So keep everything, even I'm not going to allow you to change the initial condition, it has to be a Gaussian. But how do you change this Gaussian so that you see dispersion without having to go so far in time, as Melvin correctly pointed out? Let me help you. Also, people, we're all going to sleep, and people watching the video will sleep. Let's think of it in Fourier. Right? Think of the Gaussian in Fourier. And if you have dispersion, what happens in Fourier when you have dispersion? This is how I'm thinking. As we move on to higher frequencies, what happens when we have dispersion? The phase speed changes more and more, right? For this problem, it depends on the problem, but for this problem, the higher frequencies propagate slower and slower, right? And in particular, to see that, you have to look, and that you don't have in your mind, you have to look at the dispersion relation of this problem, which, because of the cross derivatives, xct, is a PDE approximation, blah, blah, blah. But okay, believe me, right? The higher frequencies start moving slower and slower. So therefore, let me ask you, to see dispersion, should I make my Gaussian fatter or skinnier? Wider or narrower? That's a more proper way, right? Wider or narrower, thinner? Let me answer. Oh, you want to answer? No, say it. Huh? Thinner, yeah. And why thinner? Because then the spectrum is wider.
Tem outro jeito de pensar, porque se você coloca fina, é como se você estivesse aumentando o tempo. Quantas ondas ela tem?
Okay, there's two ways of thinking, yeah. There's two ways. Okay, let me repeat it so the microphone can. When you make it thinner, it's like the distance it will propagate is more post-width, right? So it's like a longer, it's propagated long. But actually, I would think of it because the thinner, but the speed might be the same. See, still speed 1. But the thing is, I think as it becomes thinner, in Fourier, the spectrum is wider. So if you have higher frequencies, and those guys in the higher part of the spectrum will propagate slower, and you will eventually see a little tail. Another way of thinking, too, is that a Gaussian, which is thin, is not quite like a discontinuity, as you saw in that exercise with the Heaviside function. But it's something that varies very fast. And if you had a jump, you would have maybe oscillations appearing there, right? Or diffusion, so on. So the way to think of it, the better way, I think, is to think about the spectrum being wider, okay? So those are things. Okay, very good. Excellent exercise, because I saw all of you thinking and thinking in the right direction. Okay, so now let's put the variable medium. Oh, and this one is just an example now where we used an approximate solitary wave, and we were able to see that with our numerical method, we could make the solitary wave travel as a traveling wave, not changing shape. So there's a very good balance between between nonlinearity and dispersion, which are not so small. Look, 0.3 is not so small. Okay. So here is a case for, here it is. Now we force beta to be 0, just to be on the safe side. So we wanted to basically illustrate numerically Berlian and Burridge paper, which they didn't do this numerically. They did the theory, but didn't do the hyperbolic case. And here we see, on the top, we see a Gaussian, the initial condition, and the profile after it propagated for, I don't know, for a long time, for 20, I think, pulse widths. Yeah, for 20 pulses, and it's right on one on top of the other. Then the bottom one is basically our exact, not our exact solution, but our theoretical asymptotic approximation, which is a Fourier integral, and the numerics. And you see one on top of the other, okay? The second one is with a detail I mentioned last time, but I'm not going to get into detail here so I can finish the class showing more stuff. So this is the hyperbolic case. Now let's go to the dispersive case. Here it is. With a little bit of dispersion, now I have convinced you that flat bottom with dispersion, it's right on the money, right? It's correct. Now it's with a disordered topography, with a crazy random topography. And the top figure is to show what would have happened with a wave if it was in the flat bottom case. It would have a little bit of dispersion, right? The tail, the airy tail. So the top one is flat bottom, which we already checked that. Now the bottom one is the formula that from Juan Carlos' thesis compared with the numerics. And it's quite amazing how not only the wave is exact, but the oscillatory guy behind the wave is also very well approximated by this theoretical Fourier integral, which I didn't give you the details because it would take too much time in this course. It's something, even in the PDEs course, sometimes I give it as a reading exercise rather than give it in class, okay? But look how amazing it is. So that's one thing that amazed us. So there's actually a story, there's actually a true story that I say that Juan Carlos, when he showed me this, he was very excited by having the pulse shape perfect. And I think he got almost a little mad at me because I wasn't paying attention to what he was showing to me, because I was already amazed that this part here behind the wave was also very accurate, right? And then I told him, Juan Carlos, because when he showed me the first graph, it was not this big. It was just basically a little window around the wave and a little bit of oscillation behind. And I said, Juan Carlos, this oscillation, he was very proud, of course, of the wave being correct. I was very happy, but I was caught by surprise. I said, this little tail behind the wave, is this the theory and the computation? He said, yes. I said, can you make this tail bigger? He said, sure. So he came with the graph with the tail bigger, and I said, wow, the theory, and this is amazing, the theory, which is designed for the wavefront, was also pretty good behind the wave, right? And sometimes that happens with asymptotic theory. And sometimes asymptotic theory looks like epsilon has to be very small. We write it, oh, epsilon much smaller than 1. And sometimes, you know, it doesn't have to be so small. I mean, you have to sometimes try. And this is a very nice thing to do when you have a nice numerical method, is that you test it for what it is designed for. And then after you have a series of good results where you're already guaranteed that you can show it in your paper, in your thesis, and so on, then you can explore and violate a little bit, just a little bit, slowly violate a little bit the regimes. And sometimes it still works in a reasonable way. And this is what we did. Okay? So I was amazed how the tail, which we call in English the coda, which is the tail behind the wave, was very well captured by the theoretical formula. So this was very nice. So then I said, okay, do you want to say something? No. So then I said, okay, Juan Carlos, let's play with this. I mean, let's go beyond what the theory was designed for. The theory is designed for a linear equation. Let's put a small solitary wave and see what happens. Okay? I think that might be our next graph. Let's see. Because a solitary wave is a nonlinear wave, a weakly nonlinear wave. Okay, so here is just one with what? What am I doing here before I answer? Specialists. What are we showing here to our audience, to the referees? The top figure is the figure for the flat bottom, and the bottom one is for the disordered bottom. So what am I trying to, what are we trying to show the referee here, or the readers? So here we're showing that actually the dispersion can be stronger. Look at the tail of the case, and it's still working very well. It doesn't have to be such a small dispersion, even though the parameter is small, but the dispersion is varying. And then here, here is for the solitary wave. So soliton propagation. So up, the first figure is for the flat bottom, and the figure below it's for a small soliton, so with a very weakly nonlinearity and a weak dispersion. Look, alpha is 10 to the minus 3, and beta is 10 to the minus 3. Okay, but look, alpha and beta, they look small because they're 10 to the minus 3, both of them, but actually they're not that small. They're not that small because dashed line, see, it travels 100. Why they're not that small? Let me ask the experts. Why can I convince you that actually, let me help you, alpha and beta are actually fighting against each other, and there is a technical tie. Let me help you, because also we're going to run out of time. If the dispersion was by itself, I would see an oscillatory tail, right? And the fact that I do not see an oscillatory tail is because the nonlinearity, even though it's small, it is competing against the dispersion, and it's generating a solitary wave, meaning a traveling wave. That's what is shown in the first figure, okay? And in the second figure, what we see is that, wow, our formula is working also not only for the Gaussian, it's working also for the solitary wave. And then we change the parameters a little more. Let me check the next one. I don't remember off the top of my head. Oh, this is also just to show that the theory of some other people, not Burley and Roach, the probabilistic theory said that actually the shape of the wavefront was nearly deterministic, but actually the tail depended here. So here we did You see, the last sentence, the transmitted pulse shape is effectively deterministic. That means for a certain class of random topographies, the shape, the apparent diffusion is deterministic. But the coda, no, the fluctuations depend on the medium you have sampled. Okay? So here we show, see, the front is pretty much the same. And let me see what is the other figure. I didn't remember this one. Okay, and here's just to show, and this is also good to show, maybe I'll finish in this graph. Let's see, I'm almost finishing. And this is also good to show, I like doing that for the referees, you know, for the readers. When I say referees, it's refereed because you want to get your paper published. So you first have to, you know, get the specialists to like the paper. And also for the readers, which is this. We were surprised, I was very much surprised that the asymptotic theory worked better than expected, right? As I showed you. But also, I think it's healthy to show that you cannot get away with everything, right? I mean, there's a point where the asymptotic theory is not going to work anymore, right? So you keep on pushing, keep on pushing, keep on pushing. You're very happy because it goes beyond where you thought it would go. But it's very nice to sometimes show one picture to show, look, I've reached the limit of the asymptotic theory. Now it's not working so well. But still, it's interesting. It doesn't work so well, but it's interesting. And that's what I want to show you. Look, here, now the parameters, it's a solitary wave. Let me go here. Sometimes the mouse. Okay, so here, you see alpha and beta are not that big, but not so small. I mean, the solitary wave for the flat bottom is a traveling wave. And here in the bottom, we have the dashed line. Solid line is the theory, and the dashed line is the numerics. Okay, and you see that actually the wavefront is not matching so well anymore. Okay, which means then the linear theory is not working so well anymore. Surprisingly, the coda is not so bad. Okay, and actually to wrap things up, I'm really finishing this paper now. How would I interpret this in words and with my acquired mathematical intuition from this problem? Is that, okay, we went a little too far now, but look what happened. The fluctuations behind the wave are small. So they're kind of in the linear regime, and the Fourier integral was able to capture it quite well. You see, it's not right on the money, right on top of each other, but you see the dashed line, the solid line behind the wave is not so bad. And the code, the numerical method is nonlinear. The theory is linear. And look how interesting. The nonlinear numerical solution is starting to break a little bit. The dashed line is starting to steepen a little bit in front of the solid line. Okay? And the interpretation we have here, which kind of we play with this, is a proper interpretation, is that now for this regime, alpha and beta, which means the nonlinearity and the dispersion in the numerical method, one of them is winning the fight, slowly winning the fight. Because, right? And who's winning the fight is the nonlinearity. And there's one thing that you can see in some papers, here we don't show this, we just mention it, is that sometimes also the numerical, the topography can change the effective dispersion because it basically reflects high frequencies back. So it looks like the wavefront is less dispersive than it should be. And that's why basically the wave is starting to break slowly, because now, since the high frequencies are being filtered, as we talked last time, because high frequencies are reflected back, the wave then at this stage of the dynamics, effectively, it's like it's more nonlinear than dispersive, and then it starts breaking slowly, and that's why you see the numerical solution tilting forward, but the theory is not able to do that because the theory is a linear theory. So this is a nice graph, and I think the referees like, because it shows that, look, you cannot get away with crime, right? I mean, of course, you cannot do beyond what is designed to do. Sometimes you can go a little further, but there's a moment where things stop. And I think it's very healthy, and I think it's actually very interesting. I like that very much, to put in a paper, a graph where things are not exact, because, it's basically borderline of where the theory is working, right? So it's very good. It's very healthy mathematically. It's very healthy in terms of the application for you to know how far you can go. And this is a graph that shows that. Let me just make sure there's nothing more, and then it's a very good time for us to finish. Okay, here it's other stuff. Yeah, I'll finish here, and then next class I have another paper which will have some numerical flavor to it. And what is it? I'm going to show you. I'm going to compare the equations without the conformal mapping with the equations with the conformal mapping, and we're going to see what happens. Okay, and then soon some of these classes I have to decide when. I will also show you some information on how to do this. Use this free conformal mapping software, which is very nice, very well done, and so on. Okay, so here's a very good place to stop.